There, 12:35. That's like barely late. You know, that's like the going rate for the semester. Every week it sort of creeps until we get to the point where we're at. But I will start off with some good news. So 13 out of 20 of you have completed a course evaluation. Do you remember my deal? What's the deal, folks? Anyone? What's the deal? That's right. If 18 out of 20 of you do it, you get an extra credit point. And note that I am giving you additional compensation for your opinions, regardless of what they may be. So you can take your extra credit and nuke me if you want to. That is within your rights. But I do hope to get feedback from as many folks as possible. That gives me a sense that the opinions are not just a select subset of people who had, you know, either good things to say or bad things to say. These types of evaluations are often very polarizing in that regard. That's what I'm hoping to avoid. So if I have a very high response rate, then I feel like it's a good sample of the class population, as it were. Folks are having fun on the last day of classes here outside. So woohoo, I know, right? So are we. Not to be outdone. The other class is beating you, though. So if anyone is feeling competitive, make sure you nag at least 5 of your friends, because they only had to get to 11, so we just need one more for them to hit. All right, what else did I want to show you over here? Yes, so just reminding you of what is forthcoming. This is our last day of class together, like period. We're not meeting next week during finals week. Anybody who has not turned in homework 5 or homework 3, I think everyone's gotten 3 done, but there's a few folks who haven't turned in 5. Please turn that in by Friday so you can have guaranteed feedback. After that, I will grade it as fast as I can, but I can't guarantee to turn it around in time for you to have a chance to do a revision. So just that's my internal deadline. Office hours next week by myself only. Note the time has moved on Monday to 1 to 2:30 instead of 3 o'clock. But then 12:30 to 3:30 on Tuesday, 3 to 4:30 Wednesday, and 12:30 to 3:30 Thursday. And then I'll be on email, of course, checking in with folks who are trying to get stuff done. Everything's got to be in by the end of finals week. Everything. I don't do incompletes. I've given out maybe 1 or 2 incompletes in my life for somebody who gave birth early. That's a good reason to be incomplete. And someone else whose wife gave birth early to twins and ended up in the hospital NICU. So those are reasons to have an incomplete. So those are the only examples that come to mind where folks were able to complete it within a reasonable amount of time. Otherwise, you're just shooting yourself in the foot, because the longer you get away from the material, the harder it is to complete it. So just get as much done as you can. Doesn't have to be perfect. Just give it a shot. I'm happy to help if I can. Yeah, so anything I'm forgetting? Logistics-wise, announcements? No? How's homework 6 going? It's so-so? Yeah, do you have any questions?
The only part that I can't seem to get it all, and I think it's just because I'm doing the math wrong, is the finding the test at the beginning. The first part's the test statistic and the p-value. Calculating those, is that where you have to, in the slides, it has like the nested models?
Yes, so if you're in the CFA sections, which I think is 1, 2, and 3, memory serves, yes, that is where you would do a rescaled likelihood ratio test. The invariance example that goes with that is 7A. There's a spreadsheet that you can adapt and follow pretty directly, so you don't have to recreate that wheel yourself. And please do input all of the decimal values that are given for your scale factor and for your chi-square test statistics or your log likelihoods, because it does make a difference. In this homework, I'm checking to 3 decimal places if memory serves, because otherwise the numbers get to be too similar to each other, and you can stumble into an incorrect answer just by coincidence sake. And then model comparisons in the IFA section are done via diff test, so you don't have to compute anything there directly. Any other homework questions? Right now? Not right now? Not right now? Okay, fair enough. And I'll close out of that. And we can go back to our SEM finale. Yay! Do you remember the one new word you had to learn to be able to do a structural equation model? Has 2 letters. On, yes. On is how we get slopes, directed effects. So if I go back to the picture where we left off with, we fit all the measurement models last time. I also outputted factor scores and computed various reliabilities that we'll use today. But this is a picture of the structural model that we are trying to estimate. This is from my dissertation data, where I have age as an observed variable centered at 75, mind you, because otherwise the intercepts of my latent factors that it's predicting would reflect the expected factor score for a newborn baby, age 0. Not super helpful or informative, so I'm centering predictors the same as usual. The rest of these predictors, a vision factor and an attention factor, those are already mean-centered because they have a mean of 0 in terms of identifying the factors, so I don't have to worry about centering those. So ons are how we connect a predictor to an outcome in a directed fashion. So those are regression slopes. That's exactly the same as what you learned in your first regression class. They have unstandardized versions, they have standardized versions. Synonyms for these, when you have one variable connecting another, people will call this a direct effect within this context. They will also call it a path or a path coefficient. It's an edge within the other thing, DAG, I forget what it stands for now, but so it goes by lots of names, but it's just a slope. So it's the idea that one thing predicts the other. This structural model, as we discovered last time, is saturated, meaning that there is a connection directly between every single pair of variables. So this is as good as it gets with respect to the structural model. So anything I would do to take parameters away could potentially make it worse, and that's a model comparison that I would want to do. So I put on here, these are the standardized results from the first model that we looked at where this is saturated, and we can go through and review the code if that would be helpful. Do that again. The new on. So for your structural equation models, you would build your measurement models first. So that's this whole section on this page. This is page 7 of example 9. And each of these factors is identified by fixing a marker item loading to 1. That way its variance is estimated and it can become leftover variance after being predicted by age as an observed variable. Processing speed does not have a measurement model underneath it. It has a box. So right now, all I've done is move the information in the observed processing speed measure over to a circle. I have not corrected for unreliability or any of that because the way this variable is measured, there is no such thing. It's not a scale. It's a performance measure of how quickly people are able to do a various tasks, I should say. Question? Yeah.
Why do you do that?
There is no real reason to do it. Okay, it's a semantic distinction, but there are 2 reasons why I did do it. One is in terms of just the interpretation of the figure. Age, vision, attention, speed, and driving are like the constructs that I want to focus on the relations between. And like visually, putting it in a circle makes it look more that way, as opposed to having another box here that's just an observed measure. Practically speaking, it's because I am going to show you a couple alternatives to this model in which we are using factor score estimates to indicate each of these traits rather than a measurement model, and then we can correct them for unreliability. So then I can reuse the same code when I have those variants of the model. Yeah, so there's not a good reason. It's semantics, essentially. The structural part then, our new keyword on, this is M+ code. It's always Y on the left-hand side and X's at the predictors on the right-hand side. You cannot switch that. In other software packages such as Stata and SAS, I think, Procalus, you can have your arrows go either way, but in this way it's always Y on X. So the way that I remember that is to think of an on as an equal sign. Because when you write an equation, it's always Y equals the predictors, and so it's in the same order in this case. Out here, are these labels, constraints, or both? One vote for labels, one vote for both. So how many different relationships does this line of code request? 4. I have 1x and 4 y's. So this is a multivariate regression of age predicting each of these things, and it's a latent regression because these are latent variables. And because there's 4 of them, and I've got 4 labels here, it's not a constraint, it's just a label. The reason I am doing that is so that I can estimate a couple of indirect effects and show you how that works. Likewise, how many relationships are requested in this line of code? 3, thank you, Zoomers. Yeah, they're faster than y'all. I'm watching. Whichever enters my peripheral vision most quickly wins. 3 of them, so these are also just labels. And then I have the last 2 down here, speed and attention predicting latent driving impairment, and I've labeled those as well. So we haven't really talked about direct and indirect effects much in this class. I cover that in the path analysis unit of generalized, and you may have had that in other courses. Is that something we need to talk about a little bit? Are you comfortable with direct and indirect effects as a concept? Fairly comfortable? Yeah, the idea is like if you have your mediation triangle, and X predicts M and M predicts Y, then the extent to which the relationship between X and Y differs after you control for the mediator, a test of that is whether the indirect effect of these 2 slopes multiplying each other is significant. So I have requested 3 different indirect effects. I have, let's see, age 1 is age predicting vision, and then vision 3 is vision predicting driving, yes. And so then this, putting it together, indirect effect of age to vision to driving. So I'm asking the question, to what extent does the relationship between age and driving differ after we control for visual impairment? That's what I'm asking. If that indirect effect is significant, then there is a different relationship between age and driving after controlling. Same thing of age to processing speed to driving and age to attention to driving. So 3 different indirect effects. Within M+, there are other automated ways to request indirect effects. So there's a model indirect command that will spit them all out for you without you having to figure them out. However, that is only available for certain kinds of models. They have to be all multivariate normal single level analyses to be able to use that option. If you have anything else, you have to do it manually like this, where you're literally asking for the multiplicative result of these 2 paths together. So that's a little bit about indirect effects. It's the idea of, after controlling for the mediator, does the effect of X on Y change? That's the question. To me, mediation is nothing more than regression with a better marketing campaign behind it, because that's the exact same question that unique effects would answer in a regression, but this sounds fancier. And be very, very, very careful in trying to make any kind of causal attribution out of your indirect effects. You will get hammered because we do not have the design considerations to make any sort of causal inference here. What we have is a correlation matrix, and we're breaking it up into various pieces. So there's a whole literature on mediation and causal inference within cross-sectional designs and observational designs. This was not an experiment, so tread very carefully in your wording on those, just word to the wise. Okay, so I think we looked at some of this output last time. With respect to model fit, we're still in reasonably good shape. With respect to RMSEA and CFI and TLI are, they're kind of meh, but that's because the relationships among these variables are not that strong in the first place. But this fit refers almost, actually does, excuse me, back that up. It refers entirely to the fit of the measurement model. Structural model is saturated, it can't be wrong. We have not omitted anything. So this is all measurement model information for all intents and purposes. Here are my measurement model results. So we get the same information we would in just a standard analysis. We have, these are all, okay, this is the last day of class, right? We've agreed? So I get to do some softball quiz questions. What are these things? Starts with an L. Loadings. Yeah. So this, if you copy this into a table, this is not going to please your readers. They'll be like, buy what? I would relabel this as vision factor loadings. That's what these estimates refer to. And these are driving factor loadings and attention factor loadings and so on. So for instance, this one right here, for every unit more factor, vision, latent factor, the predicted response to this indicator goes up by 0.48. So this is a linear factor model. This is a CFA type factor model that's underlying these because these are all roughly continuous measures. Next up are the ONS. What are these? And feel free to read from the screen. Regression paths, yes, otherwise known as the slopes. So it's y on x for each of these. So are vision and attention related? First column is estimate, second column is standard error, third column is test statistic, fourth column is p-value. Are attention and vision related? Is anyone feeling brave? Want to put the coefficient in a sentence, 0.287? I think I see people typing. I really want the dots. Makers of Zoom, can you give me the dots to know that someone's typing in the chat? Because then I can just like wait anxiously to see it. For every 1 unit increase in attention, vision goes up by 0.287. Right idea, but it's backwards. So it's y is right here and x is right here. So it's for every 1 unit increase in vision, y attention goes up by 0.287. Now the tricky part of this, what's a unit? I don't know. I'd have to go back to my measurement model. So a unit of vision, let's see, it's the amount of variance that is due to the factor in the far vision indicator. If I come down here, I can get, I don't think I printed them. Looks like I truncated part of my output. The variances that go with that is what you would have to know to answer that question. So the variance of the latent variable puts the units on it. So you'd have to know what a standard deviation is, for instance, to know like how much a unit is, but it's not 1 because we estimated the variance instead. How about vision and speed? Are those related? Not by conventional standards. How about driving? Are those related to my predictors? One of them. Yeah, just to attention. So these are all competing against each other for unique variance, the same as in any kind of linear model. Each of these represents the unique effect of that predictor after controlling for the others. So uniquely, for every unit higher attention, the driving latent factor goes up by 0.37, and the other two are not significant. What about age? That's the next set here. Does age predict stuff? Some stuff. So these are all scaled so that higher values indicate greater impairment. So for every year older you are, your latent factor of vision is higher by 0.02, so you have more visual impairment is the way this is scored. For every year older you are, your attentional impairment factor goes up by 0.06, and those are both significant at the traditional levels. But age is not uniquely predictive of processing speed or driving. So this was the thing that I was most interested in here. Age ain't nothing but a number. Once you control for the functional difficulties that are correlated with age, age itself does not have much explanatory power. Yes, preach. Says the old person who's sitting in front of you. These are residual covariances, so these are going to be the leftover parts of each of these variables. This is from the measurement model, and this is from the structural model. And last but not least, indirect effects. So one of those is significant, which means that the relationship between age and driving is mediated by attention. So age has a different relationship in predicting driving, before you control for attention versus after. That's what this means. Standardized solution is next, and so these are in a correlation metric. Standardized slopes, these might be called as well. People like to look at these because they're on the same scale, so you can get a sense as to what is relatively a bigger predictor of something. And that's it. In terms of R-square, though, so my model fits reasonably well. I have some significant things to talk about, but overall, how useful are these variables in predicting each other? This is effect size. So vision has a non-significant R-square. It's being predicted by age only. Driving has a significant R-square of 0.5, so this model accounts for about half the variability in the latent factor of driving impairment. Attention has a stronger R-square relative to vision and processing speed being captured by age. So these are the same kinds of R-square measures that you would think about in a regression model, just in latent land. Okay, how are we doing? Yeah. See, this part's not so bad, right? Once you get the measurement models built, then it's just multivariate regression again. So what if I wanted to test whether there were still direct effects of age and vision in driving? Well, I can take those out. So I fit a reduced model in which I eliminated 2 of the paths, from age to driving and from vision to driving. So if I take things out of my model, can it fit better or worse? If I take things out, in an absolute sense, can it fit better or worse? Worse. So if I'm looking for support for my hypothesis that you don't need to have age or vision predict driving once you have them predict the stuff that does predict driving, then I'm going for not worse. So I pick up 2 degrees of freedom. The rest of the model fit is largely unchanged because it predominantly reflects the measurement model. But I did do a likelihood ratio test, I'm pretty sure. So did making those 2 paths set to 0 make the model fit worse? It did not. So I can take them out, and it does not change fit, which means I'm still adequately recreating the relationships among these variables. I don't need those direct paths in doing so. There you go. So all of these relationships that are in the model right now are linear and additive. What if I wanted to test something that was interactive instead, or non-additive? Could I do that? Like theoretically, I can do that, right? You can have moderation, especially within structural equation modeling. You can do anything you want in that. But each of these predictors, go back to the code at the front here. Age is a predictor, vision as a predictor, and then these 2 predicting driving, they're circles. So I can't just add an interaction term to the model in the usual way, which would involve multiplying columns of observed variables together to create the multiplicative combination that the interaction term would go with. So I instead have to fit what is called a latent variable interaction. There are very many ways to do this. I would say the way that has been shown to work best is this approach that's built into M+. Alternatively, people will sometimes take their indicators and create interaction indicators by multiplying them together and then making a new factor out of that. Don't do that, that's bad. There's too many permutations of ways that you could interact things, and they don't all turn out to be the same. So latent interactions, I did not find within R's Lavon package, so the example that I built that corresponds to this stops there. I'm not going to say it doesn't exist, only that I couldn't find it. If anyone knows better, please let me know. But to do this, I'm going to switch to a different set of options for analysis. Type equals random, because technically this becomes a random slope, and algorithm equals integration. So rather, standard maximum likelihood does not need integration until you get to either predictors or outcomes that have link functions, so generalized versions of these models, or mixture models, or latent variable interactions. These things change the method of estimation. To do the latent variable interaction in code, it looks like this. And those of you who are in the advanced longitudinal class, I know there's a couple of you, and we did random slopes in M+. It's the exact same code. It's the exact same set of ideas. So the first thing that I'm doing is naming my new circle. So I'm building an interaction term between attention and vision as this example. So I called it vis attention, because why not? And then the bar, the vertical bar, is like a definition. Like, how am I making this? How am I defining it? And then X width is how you make an interaction term out of two existing latent variables in the model. So this is now a new circle that's going to predict my driving outcome. So I ask for that new interaction term to predict my driving latent variable in addition, which means that I'm allowing the effect of vision on attention to depend on how much, I'm allowing the effect of vision on driving to depend on how much attention you have. I'm allowing the effect of attention on driving to depend on how much vision you have. So maybe it's extra bad if you don't have good of either, or maybe they compensate for each other in some way. And can you guess what this stuff is? Trying to figure out what my interaction term means by requesting simple slopes as follow-ups. Yeah, so within the model, each of the main effects of vision and attention in predicting driving is going to be specifically when the other moderating variable is at 0. So as is customary in trying to understand how interactions work, what I wanted to do is ask for the slope at plus or minus 1 standard deviation of each variable as the moderator in addition. But I got to figure out what a standard deviation is, right? Because these are latent things. So I went back to the previous saturated structural model, and there's a command called tech4 that you can add to your options for output, and it told me that the factor variance that was estimated from the overall model were these values right here, and so then I am using those in the model constraint code here that's computing simple slopes. So the way that this works is vis3 is right here. That refers to the slope of vision predicting driving. So if I want to know what that slope of how vision relates to driving would be at a low value of attention as the moderator, then I start with the slope and I subtract from it the interaction term, so that label right here, times minus 1 standard deviation. So the values that go in here are what you want for the moderator. So who is the slope for? This is for somebody who has low attention. This is for someone who has high attention. And then this is the slope of attention instead for somebody who has low vision or high vision. So it's the exact same set of logic and ideas and procedures as you learned for observed variable interactions, just with this additional code for latent versions. Okay. Questions on that, or anything that you want me to say differently or again? So watch what happens to my fit when I add the interaction term. Do you think it's going to get better or worse or stay the same? Well, I'm adding stuff, right? So if we follow the principle of adding stuff can make it better or not better. Here's my results. Where'd the rest of it go? I'm the hoe, here's me. But I don't have the H1 log likelihood anymore. And because I have my own log likelihood, I can get AIC and BIC, and these are always in smaller is better. Bigger is better for log likelihood, but I don't have nothing to compare it to. The reason is that the saturated model no longer is the answer key. I've added in this additional latent variable interaction. There's no like observed data analog as to what that should be, like there is for every other observed measure in my covariance matrix. I don't have a saturated model anymore. So that means everything else is out the window. So the answer to the question is, did it help? I have no idea. All I can do is look at the results for that new term and then make an inference accordingly. So here's my new interaction. Wah, wah. It's non-significant. Worth a shot, though. So now, in terms of interpreting the rest of the results, just for pedagogical purposes, this is the slope of vision predicting driving, specifically when the moderator of attention is 0. Likewise, this is the simple slope of attention predicting driving when the moderator of vision is 0. And the interaction term is going to moderate both of those. So let's do this one. There are 4 kinds of interactions in the world, folks. They take your main effect slopes and they make them more positive, less positive, more negative, or less negative. That's what they do. Doesn't matter if we're in observed variable land or latent variable land. So if I start with the slope of attention predicting driving as a positive number, it is significant, conditional on a vision factor score of 0. What does this interaction term do to it? Which pattern is this? And I'll zoom in further so you can see the numbers. The interaction term is also positive. More positive. So does it make the effect of attention on driving stronger or weaker in people who have higher vision factor scores? Stronger. Yeah, so more positive or more negative means the effect is strengthened. It's moving further away from 0 in either direction, whereas less positive or less negative means the effect is weakened. If I went the other way, I would say that the interaction term is making it less negative and then heading into the positive side. So that one is a little bit harder to describe, but that's where the simple slopes come in handy. So the first 2 are the slope of vision conditional on low or high attention. So it looks like, yeah, it's negative at the low levels. It crosses over in past 0 into the high levels, but it's either of these simple slopes is not significant. Here, we have the effect of attention at low vision, which is significantly positive, and the effect of attention at high vision, which is also significant and more positive. So yeah, it's making, the pattern is such that having higher vision factor scores strengthens the relationship between attention and driving. And you thought you'd go a whole semester with me without an interaction term? You're mistaken. Question?
So why are the A4 low and A4 high significant if the interaction isn't significant?
So these are talking about the slope of attention predicting driving sort of spliced at different points of the moderator. And the interaction being non-significant means that the difference between these as you go up 1 unit is not significant, but these are not being compared to each other. They're each being compared to 0. So they're both significant and positive. The interaction says that there's not a tendency of a linear increase in the slope for each unit of the moderator. So these are just both positive numbers. Significantly different from 0, but not necessarily from each other. That better? Maybe? Okay. Probably? Okay, I'll take probably. So yes, you can do any kind of moderation analysis that you want with latent variables or observed variables. If one of these predictors were observed, it would still be a latent variable interaction. So if you have a circle and a box and you want to interact them, it's a circle. It's rules. Okay, I think, yeah, okay. We're ejecting from this. So I want to go back to the slide deck and see how far I can get. Not going to get through it all. But the last couple models are meant to illustrate what your choices are if you have a very small sample and you can't make the entire SEM you want run at once. That is a very realistic concern. In Bayes, maybe it will fix it and maybe not. If you want to know if Bayes will fix it, you know what you can do? You can sign up for Jonathan's class in the fall where he's going to do Bayesian SEM kinds of things. Then you can learn how much Bayes can fix it or not. I know a couple of you have. Plenty of room, though. All right. Okay, so this is, yep, slide 11. I have lecture 9 here. So what can I do instead? The whole point of SEM is that you don't have to output factor scores. You can keep the variable latent and examine the relationships of how your latent variable relates to those of other measurement models, either latent variables, observed variables. That's the whole point. But it may not work, meaning not converge at all or otherwise give unreliable results if you have relatively small samples, especially if you have a lot of parameters you're trying to estimate. If you have any kind of link functions in your model, so that increases the demand in terms of estimation, so generalized outcomes, IRT measurement models, that kind of thing. Many latent variables are included, especially with link functions, so that's the especially bad combination. The latent factors are not locally identified, so if you only have 2 indicators, that might work, but it's not a great idea. You're more likely to have problems because that latent factor is not going to stand on its own. If you need latent variable interactions, so what I just showed you, you probably can't have more than maybe 1 or 2 of those in the model at a time. You can't test interactions with everything because it requires numeric integration. So the same kind of rectangling that the IRT models under full information required, it's the same idea. And then what to do next? So I had some alternatives on here. Earlier this semester, I attended a talk by the creator of Lavon, Rossell or Rosseel, I'm not sure how to say his last name. And so I put a link to his talk and the corresponding Lavon code. He and his colleagues are developing some alternative 2-stage estimation routines for these things. It's called, I think, SAM instead of SEM as part of Lavon. So you can check out those as some things that are currently in development, but I just wanted to go over some stuff that people do and what the potential downfalls are. So there's really 2 main problems when it comes to trying to represent latent variables with some kind of observed information. So one is that if you're using a sum score, that assumes unidimensionality, which you would have already tested by fitting your measurement models, but it also assumes parallel items, that all of your items are equally discriminating and that they all have equal error variance. And if you're working with an IRT model where you don't have error variance, then it still would just be the equal loadings part. So factor scores are only equivalent to the sum scores under a parallel items model. That's the only case in which if you summed items up and you estimated a measurement model, the factor scores would be perfectly correlated with the sum scores only if that measurement model holds all the loadings equal and all the error variances equal. And here's a paper on your reading list that talks all about it, right, Erica? Yeah. And then there's 3 follow-up papers after that for a whole discussion if you're interested. But otherwise, a sum score is logically inconsistent with the factor model that you fit, which is usually congeneric, separate loadings and separate intercepts and separate residual variances. Observed variables also assume that the trait is perfectly reliable or known exactly, that its standard error would be 0, and that is never ever going to be the case. If 0 variability of the estimate is assumed, then the standard errors for how that variable relates to other thing are going to be too small. So your relationships are going to look rosier than they should be. And if reliability is not perfect, then the estimates could be biased by differential reliability across variables. So if you pretend everything is perfect, the ones that are much less perfect will have more incorrectness in terms of their conclusions than the ones that are less. So here's another paper about that I think is on your reading list too, and if not, you have a link to where it would be. So I want to just briefly talk about a couple different strategies from this lens as to which of these problems they have and how they can potentially solve those problems or address them. First one, parceling. So this is the idea of adding stuff up, sort of, but not all the way. So a parcel is a sum of indicators, but not all of them. So for instance, if I had 12 indicators, I might create one parcel that sums the first 4, a second that sums the next 4, and a third that sums the last 4. And so I would then have a factor model that looks like this, where I estimate all 3 loadings, all 3 intercepts, all 3 error variances, and then I fix my factor variance to 1 and mean 0 for identification. Okay, so have you heard of this approach before? A few of you have? No? Okay, good. Forget. Don't know this, okay? Because parceling is cheating. No matter what you've heard, the arguments can be easily disproven. Parceling is cheating. So if we look at what the model should be with 12 indicators, I have 12 times 13 divided by 2 plus 12 possible degrees of freedom. If I count up all the means, variances, and covariances among my 12 indicators, that's 90. If I fit a congeneric single factor model, 12 loadings, 12 intercepts, 12 residual variances, that spends 36. I got 54 left over. That's a lot of room to be wrong. That's fair. But if I fit the model to my 3 parcels, guess what happens? It's perfect. It's just identified. I can't be wrong. Problem solved. So yeah, this is cheating. So if you're interested in trying to use this, here is what I would recommend. Recognize that when you add things together, you are assuming tau equivalents equal loadings, so you can actually test that. The way to fit the model properly would be to force all of the loadings within a parcel to be equal to each other as a constraint. Then you are fitting the model that the parcels imply, that it's one thing in terms of how it relates. So you could demonstrate that as evidence that it's okay to parcel in that particular context. Otherwise, you will end up with different fit and parameter estimates depending on how you add things together. And so Sonia Sturba has done a bunch of work on this. Here is a review chapter that's on your reading list where basically it's just the mic drop on parceling. Like it's just nope, 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 nope. And they have an R package that shows you how many different solutions are possible if you parcel in different ways. Like there's 1,000,001 combinations of how you could add these items together to create fewer indicators, and which combination you use is going to dictate what happens. So yeah, no. So parceling is an intermediate choice between adding everything up and treating everything as latent. It has assumptions to it in the same way that a sum score has assumptions to it, and it can be used disingenuously to hide misfit. So we don't want to do that. Instead, simplify your measurement model. So let's say that we have our 12 indicators and we're worried about how many parameters we have. Well, one factor model fits 36. Let's say that I fit a Roche model. I hold all of the loadings equal to each other, then I'm estimating one loading instead of 12. That, by the way, is where most of the difficulty in estimation will come from, is things related to the factor loadings. Intercepts and error variances are not harder to estimate because they're already part of the observed data. Every variable has a mean, every variable has a variance. So those are easier to come by than the loadings. I could even make it simpler. So what if I had a parallel items model? Then that's one error variance instead of 12. I save another 11 degrees of freedom. And what if I can constrain all the means to be the same? Well, now I'm at, actually that one's a typo. Take your pen and get rid of that 2 there. I'll fix it after class. I get 3. So somewhere between 3 and 36 is how many parameters this measurement model would need for 12 indicators. It's up to you how many to spend. But these are ways that you can fit simpler models without having to cheat. So you can test all of the constraints that these would lead to these series of nested models. And there's also some literature with respect to IFA as to what happens when you have really sparse categories. So I know some of you had to deal with this, like you had 2 people get an answer right or something like that. Those kinds of items can be very difficult to estimate, but if you have polytomous data, there's some work that shows that recoding sparse categories into fewer categories actually works better. So here's an article on that for your interest as well. Okay. Questions on any of that? So no parceling, we're not doing that. What about single indicator models? Well, what if I want to create a box out of my factor to put in my structural equation model instead? Here's some options for that. So what I had done with processing speed is an example that is more specific than this generic one here. But let's say that I have a measure, and I don't know how much reliability it has, so I'm assuming it's perfect. I can say factor by sum score at 1. Sum score's variance for its leftover variance is fixed to 0, and then the factor has all the variance. So what this would do just by itself is take the information that's in that box and move it to the circle. Doesn't change anything, doesn't correct for anything, there's no magic there. But what if we had an estimate of what reliability should be? We could get that, right? We could fit a factor model, compute an omega for it, and then use that to try to correct for unreliability in the sum score, because omega is sum score reliability. So this is what that would look like. To remind you, here's the formula for omega. This is from a single factor model. We have the variance of the factor times the sum of the loading squared divided by all of that plus the sum of the error variances and twice the sum of the error covariances. So this is reliability of a sum score under a unidimensional model. So now what I can do is still have my latent variable have one indicator with the loading fixed at 1, but rather than saying it has no error variance, I say it has this much. And how much is this much? Whatever works out to be the unreliable variance in the variable. So how much variance it had in the first place, downweighted by the amount of unreliability, 1 minus omega. So if my omega were 0.8, then this code would say, hey, can you take whatever was 20% of this variance and put it as error variance for this variable, and then leave the other 80% and move it over to the factor? So it's moving the true part to the latent factor, and then leaving the untrue error, whatever's not the factor part, at the level of the observed variable. So this is reliability corrected sum scores in this case. This would work better than pretending that it's perfectly reliable. However, it's only possible in a CFA model because there's only one reliability coefficient in a CFA model, but how many are there in an IRT model? One or more than one? Yeah, there's a whole function, right? And it's all like bumpy and windy. So I do not know of a way to tell it to change this dynamically based on a factor score. I think there is a way. I have some research ideas about that I have yet to pursue, but I don't know of a way that has been demonstrated. So this is a CFA solution, not an IFA or IRT solution. And if you want to mean center your variable, then you would estimate the intercept for the observed variable and then fix the factor mean to 0 for identification, and then you essentially have centered it. So this is one choice. What about factor scores? I had everybody output factor scores for your homework, right? So you could make pictures. Can I just like take that and use it as data? No. So factor scores are more consistent with the model than a sum score because they would reflect the model as it was estimated to predict those. But what they really are random effects. They are estimates of central tendency of each person's own theta distribution. And in maximum likelihood, these are called EAP estimates, expected a posteriori, I think. Does that sound right? Yay, I remembered. Yay me. And this is true whether it's CFA or IRT. In WLSMV, limited information estimation, you get something called MAP, which the M stands for mode, I think, in Latin or something, but that's what the difference is. So these are not as good. They will be more biased towards the mean as a function of smaller numbers of items. And this is why, by the way, in your last homework 5, I wanted you to re-estimate the model in ML to get your factor scores and the estimates, is because I knew they should be better estimates when done this way. And the variability around these estimates of central tendency is given by the factor score standard error squared. So if you picture like each person's little distribution, the standard error tells you how wide that distribution is. So at areas of theta where there's more information, the standard errors are smaller. You have less variability around that central tendency, and at places where the information is lower, then it's more. So these factor scores, beyond just having some error to them, they're also going to be shrunken. They're going to be pushed towards the mean, especially if you have more missing data or low reliability of your indicators. So there's a lot of uncertainty here. In educational testing situations, like If you give kids hundreds and hundreds of items, your standard errors are going to be much smaller than if you give kids 8 items or 5 items, right? So it's all dependent on how reliably your trait is measured. And by the way, if you ever see this in an operating manual as a set of instructions for how to make a factor, no. I've actually seen this. No, this is not right. Look at this equation. Do you see anything wrong with this? Does this look like a factor model? Doesn't. F is a predictor, not an outcome. F goes on the right-hand side. So you can't take the factor loadings and use them as multipliers to sum the observed variables. That is not what the model means. This is a component analysis. This is what happens in principal components analysis. It's a different procedure. So don't do this either. So we can do the same thing in terms of trying to correct for unreliability of a factor score rather than a sum score, and we would use factor score reliability to do that. So factor score reliability is computed as the variance of the factor scores from the model, so like what the latent variable variance is supposed to be, divided by that plus the standard error squared for that factor score. So then we would get whatever estimate of reliability this number turns out to be and correct our observed variable the same way. So once again, it'd be like, hey, if the reliability was 0.8, then this code is saying, take 20% of that and move it to the residual variance of my variable and leave the other 80% as variance of the factor. So if you're going to use factor scores as observed variables, you can correct for unreliability using factor score reliability. If you are going to use sum scores as observed variables, you would correct for it using omega. And once again, can't really do this in IRT because it would be a different number at every point on theta. So here's an example from the forgiveness of situations subscale. I also did it in example 9, but just to remind you that you've seen this stuff before and computed it. So these are descriptive things you would report as part of your psychometric analyses. They could also inform how you would treat a single indicator as a replacement for a measurement model if you can't estimate everything all at once. Okay, questions? So reconsidering then the two potential problems with single score representations. Some scores assume unidimensionality and parallel items. So multidimensionality could be a problem. Ideally, you would want to make sure that your measurement model fits first, not just add it up. Factor scores are more consistent with the model, but they still have unreliability to them. And there's been a lot of recent work about how to use factor scores. Here's an example of that that's on your reading list. It depends on how you're going to use them as predictors or outcomes, what the optimal ways to do it is. So there's a broader literature on this sort of two-stage SEM, how to use observed things from a measurement model, go to stick it in a structural model as a replacement. So if you can't do reliability corrections in IRT and IFA, what can you do instead? One more thing, plausible values. So is anyone here familiar with NAEP, N-A-E-P, as an organization? Yeah, like that sounds a little familiar, no? They have an internship program. I know there's been a couple people who've gotten to do that, but they are one of the places that do this. So in NAEP data, each person has 5 different versions of a factor score for every single variable. What they are random draws out of the distribution that is implied if you take the EAP estimate as the mean and the standard error as the standard deviation of that distribution, and then you take 5 draws out of it. And then you do your analysis 5 times. And then you average all the results back together using the rules from multiple imputation literature, and then you get your answers. So they're not pretending that the factor scores are perfect. By having repeated draws, then you're introducing error back into it, because it's not going to be the same number every time. So there's some research on this as well. 5 seems to be the minimum in terms of how many times you would need to do this, and diminishing returns as you get more and more. I will say that this is not nearly as painful as it could be. So like in M+, it's like 2 extra lines of code to do this. And you tell it how many data sets you have for it to run through, and it will do them all. So you would build a text file that has a list of data sets, and then where you say what data file to use, you give it that text file. And then it just rolls the same analysis across all the different versions of your factor scores and then combines everything. I'm certain there's an R package for that too. There's got to be. Probably stuff in Stata as well. So I do have an example of this from an older class that I did a while back. I can send that to you if you're interested. But this is something that instead of trying to correct factor scores for unreliability as a constant, this is an alternative when you have non-constant unreliability instead. Here are the steps then. So you would estimate your factor model, and you can add S values to your output to save some typing. What that does is print all of your model statements with the values that were just estimated on them. You can feed those into something else as start values, or you can fix them. So you can then feed in those parameters, constrain them with @ re-estimate the model using Bayes, which is needed to do the drawing. Then you would merge all the data sets together to do this, or you can tell it to use separate data sets in M+, and then you can use the factor scores as observed variables. So it's type equals imputation on the analysis. So this is surprisingly not terrible, and here's the link to how I did this in an older class, one of the KU edition of this class a while back. Yeah. Slide 23, I got there this year. This is the first year I got all the way to the end. I'm so excited. And I get to even show you how it works, because I got 14 minutes left. So SEM is wonderful when you can do it, but it's not a panacea. So keep in mind that anytime you're assuming stuff is perfectly reliable, you're probably wrong to some extent. And so something besides putting in an observed sum score or a factor score would be needed to solve that problem. Here are lots and lots of choices. In example 9, I did it a couple ways. So what would have happened if we had used the mean of each person's factor score distribution from the single factor models that we fit in the first place? So earlier in this handout, I started by fitting all the measurement models. So for instance, here's one for visual impairment. And at each step, I saved factor scores from the model. So not shown in the code, but it's in the code that's online, all the individual files. So I saved all of these factor scores because I knew that I wanted to do this example. There we go. So now what I have are my 3 new latent factors for vision, driving, and attention. Processing speed was already a single indicator. I am going to use reliability corrected single factor scores. I'm going to keep the latent interaction because why not? Then all the models are the same model, so we can compare what happens. So here is the new part, right here. Rather than fit measurement models, we're tricking it. So I have vision is now my latent factor that is indicated by the factor score. Here is its residual variance, or excuse me, here is the factor's variance. Then we have the residual variance for the indicator, the factor score. The latent factor mean is fixed to 0, and the latent factor variance is estimated. So then the question is, how much is due to residual? I did the same pattern for all of these. And here is where I figured that part out. So where these numbers came from is the first part is 1 minus the factor score reliability that I computed from each of the measurement models. So that one, that one, that one. And then times the variance of the factor scores as was estimated in those measurement models. And then that much is the squared standard error. So I am fixing the amount of leftover variance in my factor scores to the amount that's supposed to be there given unreliability. That's the idea. So like this would become 20% of the variable's variance, for instance, if my reliability coefficient were 0.8. So I did that for the 3 that I could. And note for processing speed, I fixed it to 0, meaning that I have to assume it's perfect because I don't have information about its reliability. And that, Vladimir, to answer your question, is the real reason why I kept my model the way that I did. because I knew that I was going to want to draw that parallel. Here's another option. What if you're like, Lisa, this is too much damn work. I don't want to go look at all these numbers. Can I just pretend everything is perfect? Okay, let's see what happens. So what you're saying then is that you have no error variance in your factor scores. They're perfect. What I did is compare the standardized solution across the 3 different versions of the same model. The full SEM, where everything is latent that's supposed to be, the reliability corrected factor scores, or the outputted factor scores assumed to be perfect. Okay, that is 5A, 5B, and 5C respectively. And I made a table comparing all of the structural model coefficients that I would care about. So if we just eyeball these things, looks like a little bit of differences, but nothing huge. If we head over to the standard error column, we start to see a little bit more differences. So there's less smaller standard errors when you assume things are perfect, but they're not really perfect, so that's probably not right. And the conclusions that you would draw might wiggle a bit too. In this case, it looks like we would come to the same conclusion all 3 ways, but that's not necessarily guaranteed. And here's a picture that maps the parameter estimates on the left and the standard errors on the right to each of these methods. So the right answer, so to speak, is the y-axis in both of these plots. That's what we get out of the full SEM, where everything stays latent. We're not assuming anything's perfect or any of that. The red line is what we get from the model where we correct the factor scores for unreliability. And the green line is what we get if we pretend everything's perfect. Now, who do you think wins? Which one of these, red or green, looks closer to the right answer as the y-axis? What do you think? Now, note that I kept the scales the same on purpose, right? So a maximum of 0.2 for a standard error in the right model, a maximum of 0.2 standard error in the Chidi model. So ideally, if these things match, they should have a diagonal line. There should be a 1-to-1 correspondence. Who's closer? Yeah, I pick red. Green, the standard errors are way too small relative to what they would be if all of the unreliability were actually appreciated. So I think the green is cheating, a little too optimistic. So there's, like I keep saying, there's a broader literature on this, and I would encourage you to go to that if you're interested in learning more about this or learning what the appropriate shortcuts here. But the take-home message is, don't pretend things are perfect. Don't pretend they're unidimensional. Check the ladder first and try to find ways to build in the uncertainty that your factor scores or your sum scores have into your model. That's your take-home message. There. And I'm like, you know what? I'm out of time. If you want to know what a sample results section looks like for a structural equation model, you can read this paper. There it is. I did not do latent variable interactions in this paper. They didn't really exist at the time in terms of what was readily available, and I didn't do mediation because I didn't care about that then either, but the rest of it is about the same. There. How are we doing? That's it. That's structural equation modeling. You're ready to go now. You're like, what? And if you're thinking, yeah, no, I don't feel ready to go at all, that is correct. I took a course on structural equation modeling in my graduate work. It was only the CFA variety, mind you. And I remember sitting in front of my first like real task with it and just like, I don't even know where to start. So if you're feeling that way, it's okay. At this level of complexity, things take time to sink. Just keep working at it. Don't beat yourself up if you don't remember it perfectly. You have all earned the right to bother me by being here as part of my class. You can email me questions even after the semester is over. I'll try to find you resources or help you as best I can. But the only real way to learn this is to do it. Like, that's the best thing, is just to start playing with your own data, because once you see this in the context of variables you care about, things click in a very, very different way. So that would be my recommendation moving forward if you're feeling overwhelmed. Yes, that is correct, but it does get better with practice. And if you really, really want to learn this stuff, sign up to teach it. Then you will realize very quickly what you don't know. The first time I tried to teach this class in 2007, it was horrible. I was trying to learn things like 10 minutes before I presented them. It did not go well, but damn did it force me to learn this stuff in a different way. So, all right. Any questions on this material or in general? Since it's 1:41, yeah.
Anytime we want to analyze archival data using a sum score, so does that mean we need to test the loadings of these items?
So the question was, if we have archival data, is in the archival data, would you have item responses or just sum scores?
We have different items. For example, these items are not from a formal scale inventory, but you want to sum them up to have a score.
Okay, so the question was, they have items, they're not part of a formal scale, but you want to sum them to get a score. I would say that recognize that sum score is a parallel items model. What you are saying is that they're all equally related to whatever you're trying to measure and have equal error variance in doing so. And that is a testable assumption. So I would say, regardless of whether you're using archival data or brand new data, anytime you are going to rely on a latent trait, like a subscale or something, it's up to you to verify the measurement model. Like, realistically, one person and one sample fit one CFA with these items one time and it fit, and the rest of the world's like, look, it's been validated. No, doesn't work like that. Each time you use a measure, you should validate it yourself. You should check the factor structure. You should make sure that it works the way you intended. That's especially important if you have a different kind of sample than the measure was intended for. So yeah, I would say no, you can't just add stuff together. The worst outcome of that is that it's actually multidimensional and you're adding together apples and oranges, which would get you, not anything useful. If it is sufficiently unidimensional, then a sum score is probably not too far off of what a factor score would be, but it does still have unreliability to it that you'd want to control for. So yeah, every time. And no other questions right now? Then I want to say one more time. Oh, what are office hours next week? Monday 1 to 2:30, Tuesday 12:30 to 3:30, Wednesday 3 to 4:30, Thursday 12:30 to 3:30 on the website, and nothing Friday. I want to say thank you. That's what I want to say. I really, really appreciate all of the work that you guys put in this semester. I'm proud of you. I hope you're proud of yourselves. It's a journey, and the only way to get through it is together. So just thank you for being here and making the effort. So let me know if you need anything. Otherwise, have a great summer. Take care of yourselves, and I hope to see you next fall sometime.
Thank you, Lisa.
Thank you. Bye for now. Bye for the last time.